Okay, so let's continue on. This time looking at a couple of examples that do not have composite functions and how and why we're going to use U-substitution for problems like this. So for number 7, we have the integral of x cubed divided by x to the 4th power minus 1. Okay, so when we look at this, we don't have a composite function in this quotient. We just have the quotient of two functions. And there's nothing that we can do like algebraically to put 7 into a form where we can integrate using just standard integrating techniques. So the only other tool we have at our disposal is U-substitution. Okay, so in a lot of instances that you're looking at where you have a quotient, a lot of times you're going to want to let u equal the denominator of your quotient. And the reason being is that when you differentiate that function, so the derivative of u is going to wind up becoming 4x cubed dx. When we isolate dx, that's going to put that factor of 4x cubed into your denominator, which hopefully you're able to cancel with a factor of x cubed in the numerator, okay, which happens to work in this particular case. Because this integral is going to become the integral of x cubed, we're going to replace x to the 4th power minus 1 with u, and then we're going to replace dx with du over 4x cubed. So when you let u equal what's in the denominator, when you isolate dx, that's going to put that derivative into the denominator so you can cancel with your factor in the numerator. Okay, which in this particular case, the x cubes cancel, so that leaves me with 1/4 the integral of 1 over u, which we're integrating with respect to u. And then 1 over u, the antiderivative of that is the natural log of the absolute value of u plus c. And then we're going to replace u with x to the 4th power minus 1. So that's going to be 1/4 the natural log of the absolute value of x to the 4th minus 1. And then we're adding c. So most functions that you look at, like when you take the derivatives of those functions and isolate dx, that's going to put that derivative into the denominator. But if you think about some function where that's not going to be the case, for example, the natural log function, or when you differentiate inverse sine or inverse tangent, all of those derivatives are in the forms of fractions. So when you isolate dx, those derivatives factors are going to be in the numerator. So when you have a quotient that involves the natural log or inverse sine or inverse tangent, so if you have a quotient involving those functions, usually you're going to want to let u equal the functions in the numerator in those particular cases. Okay, and we'll take a look at an example like that in a second. Okay, let's do 8. So for 8, we have the integral of the tangent of x, which we are integrating with respect to x. We can't integrate tangent the way that it's written right now. Like, we don't know a function such that when you take the derivative of that function, it gives you tangent. And there's not a whole lot that we can do to like rewrite tangent. I think the only thing that makes sense as far as rewriting tangent is to rewrite tangent as the quotient of sine over cosine. And then again, we have a quotient just like we did in the previous example. So we're going to want to let u equal the denominator here, cosine, so that when we differentiate u, the derivative of cosine is negative sine times dx. And when we isolate dx, we get dx equal to du over negative sine. So This integral becomes sine. We're going to replace cosine with u. We're going to replace dx with du over negative sine. So the factors of sine cancel. We can pull the factor of -1 out front, and this becomes the opposite of the integral of 1 over u, which we're integrating with respect to u. So we have our integral written in terms of u and du only, which is what we want, so that's good. So the antiderivative of 1 over u is the natural log of the absolute value of u plus c. And then we can rewrite that as negative the natural log of the absolute value of the cosine of x plus c. But let's say we were given like this question as a multiple choice question, and that function wasn't listed as one of the choices. You can actually rewrite this function in a different way. If you use your log properties, you can take that factor of -1 and make it the exponent for cosine. So that's like saying the natural log of the absolute value of the reciprocal of cosine, and the reciprocal of cosine is secant. So either of those two ways are acceptable for writing the antiderivative of tangent. I'm going to box both of them. Both of those are acceptable. They're just different ways of writing the same thing using your log properties. Okay, for 9, we have the natural log of x divided by 3x, which we are integrating with respect to x. So again, we have the quotient of two functions, neither of which are a composite function. And I said usually you want to let u equal what's in the denominator, unless you have a natural log function or an inverse trig function, like inverse sine or inverse tangent. Okay, so in this particular case, we want to let u equal what's in the numerator, the natural log of x, because when I differentiate that, the derivative of natural log is 1 over x, which we are multiplying by dx. And when I isolate dx, that's going to be equal to x times du. So that's going to take that factor of x and cancel it with a factor of x in the denominator. Okay, so that's why in this particular case, we want to let u equal the function in the numerator. Okay, so when we do that, this becomes u over 3x, and then we're going to replace dx with x times du. So the x's cancel. I can pull 1/3 out front, and then we're integrating u with respect to u. So this is going to be 1/3 antiderivative of u is u squared over 2 plus c. So this is 1/6. We're going to replace u with the natural log of x, which we're squaring, and then we are adding the constant c at the very end. All right, for 10, we have the sine of pi x times e raised to the cosine of pi x power, which we are integrating with respect to x. Now, here we have like the product of two composite functions. So we have to figure out what we want to let u equal in this particular case. And I'm going to let u equal the exponent for e, which is the cosine of pi x. So when I differentiate here, the derivative of the cosine of pi x is going to be negative pi times the sine of pi x, which we're multiplying by dx, which makes dx equal to du over negative pi times the sine of pi x. So I picked this example because here's one where we had to use chain rule when differentiating u, because u itself is a composite function. Okay, so this becomes the integral of the sine of pi x times e to the u power And then we're going to replace dx with du over negative pi times the sine of pi x. So the sine of pi x is canceled. I can pull negative 1 over pi out front, and this becomes the integral of e to the u power, which we're integrating with respect to u. So we have our integral written in terms of u and du like we want. And then the antiderivative of e to the u is e to the u power plus c. And then the last thing we do is replace u with the cosine of pi x. All right, so we're going to do 2 more examples to wrap up this part of the video, then we'll do 3 more on the next video. Okay, so 11 and 12, like the process that we're going to use for 11 and 12 are going to be exactly the same. So for 11, we have 1 over the square root of 9 minus 4x squared, which we are integrating with respect to x. Now, when we look here, I would say that this function most closely resembles the derivative of an inverse sine function, because it's 1 over the square root of something squared minus some function squared. Okay, so when that is the case, there is a special type of U-substitution that we're going to have to do. Okay, and again, this process is going to be exactly the same for inverse sine and inverse tangent. You guys see number 12? Like that's going to be 1 for inverse tangent because we have 1 over some number squared plus some function squared. Okay, so the process that we use for both of these is going to be exactly the same. Okay, so what we want to do first here is we're going to let u equal, I want to do the square root of that variable term. So when I take the square root of 4x squared, that's going to be 2x divided by the square root of that numeric term. So the square root of 9 is 3. Okay, so again, this is going to be a special type of U-substitution for these problems. Okay, so when we differentiate here, we get du equal to 2/3 dx, which makes, when I isolate dx, dx equal to 3/2 du. Okay, but we've got to do one more thing before we proceed. Okay, so what I'm going to do next is I'm going to take this equation here, so what we let u equal, and I'm going to multiply both sides by 3. So we get 3u equal to 2x. And then I'm going to square both sides of the equation, okay, which is going to make 9u squared equal to 4x squared. Okay, so once I have that, now I'm going to rewrite my integral. So this is going to become the integral of 1 over the square root of 9 minus, and then I'm going to replace 4x squared with 9u squared. And then the last thing I'm going to do is I'm going to take dx and replace it with 3/2 du. And the reason I'm going to do that is we have 1 over, when I look at that denominator, rad 9 minus 9u squared, I can factor a 9 out of both of those terms. So I can rewrite that denominator as the square root of 9, which is 3, times the square root of 1 minus u squared, which we're multiplying by 3/2 du. So we can now cancel the factor of 3 on bottom with the factor of 3 on top. I can pull 1/2 out front, and we're integrating 1 over rad 1 minus u squared with respect to u. And that right there is in the right format that we want, because that integral is going to wind up becoming the integral of the inverse sine of u plus the constant c. And then the last thing we have to do is go back and replace u with 2x over 3. So that's going to be 1/2 the inverse sine of 2x over 3 plus the constant c. Okay, you guys will for sure have one of something that looks like 11 or 12 on your test when you take it. Okay, so I want you guys to work through number 12 using the exact same process. All right, so go ahead and pause the video. Then whenever you're done, you can put it back on. Okay, so let's take a look at this one. Again, we're going to want to let u equal the square root of the variable term, which is going to be 6x, over the square root of the constant term, which is 5. And then I can go ahead and differentiate here, which is going to make du equal to 6/5 dx. When I isolate dx, that's equal to 5 over 6 times du. Okay, and we want to do just like we did in the previous one. So we're going to take this statement here, and I'm going to multiply both sides by 5. So we get 5u equal to 6x, and then square both sides. So that's going to make 25u squared equal to 36x squared. Okay, so I'm going to go ahead and rewrite the integral now. So that's going to be 1 over 25 plus 36x squared is the same thing as 25u squared. And then we're going to replace dx with 5 over 6 du. Okay, so we can factor a 25 out from the denominator. And that leaves me with 1 plus u squared times 5 over 6 du. So we have a factor of 5 and on top and on bottom that are going to cancel. And then we have 1/5 times 1/6, which is 1 over 30. I can pull that out front. This becomes the integral of 1 over 1 plus u squared du. And that's exactly the format we want to be in, because we know the integral of that function winds up becoming the inverse tangent of u plus the constant c. And then the last thing we have to do is replace u with 6x over 5. So that's 1 over 30 times the inverse tangent of 6x over 5 plus the constant c. Okay, so I like that process for inverse sine and inverse tangent because I can use the same process for both types of problems there. All right, so we'll save the last 3 examples for the third video.